السلام عليكم شباب، مساء الخير. Today we will continue our lecture that started yesterday about the electrical systems. We will continue modeling the electrical system. Yesterday we have seen the electrical elements that we defined as resistor, capacitor, and inductors. And we defined also the rules that we are going to use to find the electrical models. So we defined the KVL, Kirchhoff voltage law, and we said the total voltage across any closed loop is equal to 0. And we also mentioned, and we have seen the KCL, the Kirchhoff current law, and we said the current entering any node are equal to the number of currents leaving the node. And we have showed you one example, which was about the modeling of a first order system that consists of just an inductor L with a resistor R. And we have seen that when this is subject to a step input, we found the response or the current output to be of this form. So if the input is a step as A, constant, the transfer function is 1 over Ls plus R. It shows that we have an inductor and resistor. The denominator of the transfer function is called the characteristic polynomial. And as you can see, the transfer function, it never contains variables like voltage or current. It just contains the physical quantities that represent. It represents an inductor plus a resistor. So we should see this into the characteristic polynomial, inductor and resistor, L and R. They don't, some students get confused and they put I or V inside the transfer function. No, never. The transfer function contains only physical quantities that are, for example, for our system here, we have an inductor and resistor. And the output response look like this one here for a step response. The exact equation is this one, and the plot is this one here. So with the time, it goes to the steady state value, which is E over R. E over R is simply equal to I, according to Ohm's law. Since E is constant, so R is constant, so I will be a constant value in E over R. The time constant, this it could behave like this, or it could behave like this, depending on the time constant. The time constant, to find the time constant, is to draw a tangent line at the origin. It crosses the final line or the steady state line at a point, and then from this point here, you draw a vertical line. This vertical line, the distance from here to here, is the time constant, which is the rate of convergence here, tau. And this time constant corresponds to 63.2% on the graph. It crosses the response at a point. This point represents 63.2 from the final value, E over R. This is the step response of an electrical system. We have another system here. They are asking you to find the transfer function, the output over the input. And you may see that we have, for example, a resistor and a capacitor, and we can see that we have two loops here, the inner loop, which is I here, and we have also the outer loop here. So if we use KVL for the inner loop for this one, we will have the voltage cross R is Ri, plus the voltage cross the capacitor will be 1 over C integral I dt, which is equal to EI. So this is the inner loop. For the outer loop, we have E naught will be equal to I integral IC dt. So we have two loops, the inner one and the outer one. Now, if we would like to take the input over the output here, because the input is EI and the output is E naught. Because of we have I here and we have integral I, it will be difficult to separate them. So just if you take Laplace transform, this will become algebraic equation. And with algebraic equation, we can deal with it very easily, and we can separate I from this and this one. So if we take Laplace transform of both sides of the first equation, when you take Laplace transform for it, it will give you R times I of S. And Laplace transform of the integral is 1 over S, I of S. So this one turns out to be 1 over CS times I of S. If you take I of S common between this and this, you will have R plus 1 over CS. I of S is equal to the input voltage, which is EI of S. So this is our input voltage. The output or the outer loop is to integrate the second equation, 1 over CS I of S is equal to E naught of S, and E naught of S is the output. Now, since they are looking for the transfer function, which is the output over the input here, E naught over EI, we can simply take the ratio from here, E naught over AI, it will give you the transfer function. E naught is simply 1 over CSI of S, and AI is simply R plus 1 over CS. You simplify by I of S, and you will find that your transfer function is 1 over RCS plus 1. As I told you, Shabab, the transfer function does not contain any of the variables. It does not contain I, it does not contain E, also the voltage E. So it is only the physical quantities. It shows here that you have a resistor with the capacitor, So it is exactly an information about your physical system. Resistor and capacitor, they are shown here in the picture. RCS plus 1, you have them here. Before I move to the next one, is there any question here? Is there any question, Shabab? Any question? Any question, Shabab? Any question? طيب. Okay, thank you. So let's move on to the next problem. Here we have almost the same idea, but we added an inductor to the previous system or previous circuit. And we do in the same way. We take the inner loop the inner loop, which is this one I, and the outer loop, which is this one here also. So if we take KVL, Kirchhoff voltage law for this one, we will have the voltage cross the inductor is L di plus dt, this one, L di over dt, plus Ri here, plus 1 over C integral I dt, plus 1 over C integral IDT, the voltage across here. So this is for the inner loop. The first equation is equal to EI. The EI is the total voltage in EI, the input to the system. The output, the outer loop will be simply, 1 over EI, or sorry, 1 over C integral IDT. Integral IDT will give you E naught. In the same way, we take the Laplace transform of both sides, provided هنا always, Shabab, when we are looking for the transfer function, all the initial conditions are 0. It goes without saying, yani. Initial conditions are always 0 when we took Laplace transform or when we are looking for transfer function. Initial conditions are 0. So if we take now Laplace transform of the first equation here, it will give you LS I of S plus R I of S plus 1 over CS I of S is equal to EI. You take I of S common, so you will get this one. The second equation, when you take Laplace transform, it turns out to be 1 over CS E naught of S. And now if you take the ratio E naught here over E naught over EI, you will get 1 over CS I of S over LS plus R plus 1 over CS I of S. Again, here you simplify with I of S and I of S, and you will find your transfer function, that is 1 over LCS squared plus RCS plus 1, which is now a second order system here. You can see S squared, it's a second order system. And you see that it contains LCR, which means your system or your circuit includes 3 elements: an inductor, a capacitor, and resistor. This should appear in your transfer function, and specifically in the denominator, which is the characteristic polynomial. That's why it is called a characteristic polynomial, because it characterizes your system. It will give you identification about the system, what your system contains as elements. واضح شباب? It does not tell you how they are connected, but at least you know that you have the 3 elements here, L, C, and R. And this is the how we find the transfer function between the output and the input. When we have, Shabab, the transfer function or blocks, sometimes we do find the relationship between input and output, either they are connected in series or in parallel. Suppose we have 2 transfer function G1 and then connected to another transfer function G2. The input for G1 is X1. The output for G1 is X2. This input, this output, which is for G1, could serve also as an input for G2. And the output is simply X3. How to simplify these 2 blocks, like we were using, Shabab. You remember the series combination for resistor and parallel combination for resistor. We did it for springs, damper, and so on. It's almost the same idea here. When we have 2 transfer functions like this, they are connected in series. The transfer function that can replace them is simply multiply G1 times G2. When they are connected like this in series, just multiply them, G1 times G2. Then you can say G1 is X2 over X1 from here. G2 is X3 over X2. And you can have G, which is this one here, G. It's X3, the output X3 over the input X1. We can write it like this: X3 over X2 times X2 over X1. We can X3 over X2, X3 over X2 times X2 over X1. So you can simplify this with this, and you are done. But here, the idea behind writing it here like this, in this form, to show you that this is G1. This is G1. And the second one is G2. So at the end of the day, you can simplify this with this, and you end up by having X3 over X1, which is the multiplication of G1 times G2 here, which is this one. This is how to simplify or how to make it just one block, reduce 2 blocks. We have another Shabab circuit here, a little bit complicated, which has 3 loops here, 1, 2, and then 3. So we have here, the current passing is I1. When it comes here, we are going to call it I2. Here, this is I2. And instead of having too many variables, I1, I2, I3, we just say, if this is I1 coming here, and this is I2. So let's say this one, which is coming inside, it's I1 minus I2, which is the difference between the 2 currents, just to have any minimum number of variables. So if we take the first loop here, we will have R1, I1, plus 1 over C1, and then the current here inside coming here is simply I1 minus I2. So integral I1 minus I2 dt, this should be equal to EI. This is for the first loop, or loop 1. Loop 1 here. Loop 1. And then the second one, we will have 1 over C1. The current is passing like this from here. So it's passing like this, like this. So it will be 1 over C1, I2 minus I1, it's on the opposite direction dt, plus R2, I2, plus 1 over C2, I2 is equal to 0. It's closed path here, or closed loop. So this is for loop number 2. And then for the loop 3, which is the outer loop here, we will have 1 over C2, I2 dt is equal to 0. In the same way, Shabab, we have to take E naught over EI, which means the output over the input. Here, the output is E naught. This is the output. And EI is the input. We take Laplace transform of all the quantities having 0 initial conditions. And then we will proceed in the same way like we did for the previous examples. So it turns out to be, if we take Laplace transform of the first equation, we have R1, I1, plus 1 over C1S, I1, minus I2 is equal to EI of S. Remember always, Shabab, remember that this is our input. And output is our, E naught is our output. So the second loop, this is the second loop, the second one will give you 1 over C1 I2 minus I1 plus R2 I2 plus 1 over C2S I2 of S is equal to 0. So this is the second loop. This is the first one, first loop. And this is the third loop, or outer one. So here, Shabab, you see that we have many variables. We have I1 and I2 variable, I1, I2 variable, and we have E naught and EI as variable also. So in our transfer function, when they are looking for E naught over EI, we should get rid of the variable. There is no variable here, no variable. We should not, because here we have I1, because here we have I2, I2, I1, I2, I1, I2, I2. How to do that? How to do that? We get rid of them. How to get rid of them? Just if we substitute from here, we solve for I1 here, from this equation 620. If we solve for I1 or substitute by I1, this is, by the way, 3 equations with 3 unknown with Cramer rule, you can solve it easily. But you do substitution also will solve for it. Now, if we substitute I1 is equal C2S EI of S plus I2 over R1 C1S, this is I1. Here, you substitute every I1 you find it, every I1 you substitute it by I2. Okay? Every I1 you substitute by this one. You substitute here, what is I1, and then that's it. You will have this equation will be only in terms of I2. In terms of I2. So this equation will be only in terms of I2. And this is I2, this is I2, this is I2, and then here I1 will be I2, as you can see here. And now you will find, because I2 here is a function of, here you have I2. So taking the ratio of E naught over EI, E naught over EI, will eliminate I2 with I2, and this will give you the transfer function, which is in this form. E naught over EI will be 1 over R1C1, R2C2 S squared, second order, plus R1C1 plus R2C2 plus R1C2S plus 1. So this is a second order equation also, or second order transfer function. And it tells you that you have two resistors, R1 and R2. It tells you that you have two capacitors, C1 and C2. That's it. We don't have any inductor here. We have only capacitors and resistors. If you go back to your drawing, you will see that we have resistor here, capacitor here, and capacitor here. So the transfer function will be function of these parameters, R1, R2, and C1, C2. They will be combined R1, C1 plus R2, C2 plus R1, C2S plus this amount, R1, C1, R2, C2. This is the transfer function of finding the output over the input, which can be written also like this. In standard form, usually we leave the coefficient of S squared is equal to 1. And I will tell you later on how we can express this one and how we can express this one. In standard form, the denominator can be written in this form here, S squared plus, this is squared, twice zeta omega ns plus omega squared n. So this denominator will be the natural frequency of the system, which is omega squared n. And this term will be this term here, twice zeta omega n here. This is twice zeta omega n, this terminal. So we have twice, this is the damping term, basically. We call it the damping term. So this is anything times S is a damping term. So this is the damping term. And this is S squared, we have S squared, We will go into details to this standard equation. It's called the second order standard equation. So this is how we can model the system. Any question, Shabab? Any question? The internet today is very slow. I am not sure if you are hearing me or not. But from here in the university is extremely slow. And I'm trying to download the solved problem. I could not upload them for you for the quiz. Shabab, there is another method. It's called the complex impedance. The complex impedance method here. It just deal like we deal with Ohm's law. It's basically, it says V is equal to voltage is equal to Ri in Ohm's law. In the impedance method, it says V is equal to Z times I, where Z is the Laplace transform of your elements. Laplace transform of your elements, if we have a constant R, that is, if you take Laplace transform of both sides here, it will be V is equal to Z times I of S. V of S will be Z times I of S. As simple as that, because this one will be a constant. So you take Laplace transform of the variable here, take Laplace transform of the variable here, and this one will be, if we have a resistor connected to the resistor only, V is equal to Ri, V is equal to Ri. If we take Laplace transform, we have a resistor here. V is equal to Ri, V is equal to Ri in time domain. If we take Laplace transform of both sides, it turns out to be V of S, because this one will be variable, is equal to R times I of S. These are, we call it impedance, and we just substitute it by Z. So in this case, if this one can be written like this, V in S domain will be equal to Z times I of S. So we can see that R is equal to Z. R is equal to Z. Resistance هي نفسها Z. It's Z, exactly the Z. So this is what we are writing it. E is equal to Z times I of S. Or when we have the capacitor, when you have a capacitor, if you remember the voltage across the capacitor, can anyone remember what is the voltage across the capacitor, Shabab? We defined it in earlier our notes. This is a capacitor, and there is a current passing through I. So we define the voltage to be V is equal to 1 over L, 1 over C, integral I dt. Do you remember this, Shabab? 1 over C, V is equal to 1 over C integral I dt. Now, if we take Laplace transform of this, it will be V of S is equal 1 over CS I of S. Now, if you compare this to this, these two equation here, what will be Z, Shabab, hina in this condition? So voltage hina in the left-hand side is voltage on the left-hand side. I on the right-hand side, I on the right-hand side. So what will be Z, Shabab? Z will be what? Z, can anybody, what will be Z in this case?
1 over CS. 1 over CS.
There is a student talking, but I did not hear his name. The Z in this case, Z for the capacitor, it will be simply 1 over CS. 1 over CS. This is when we have a capacitor. If we have an inductor, if we bring an inductor here, Shabab, and we are dealing with an inductor like this, this is our inductor, and we define the voltage to be L di over dt. So if we take Laplace transform of both sides here, this turns out to be V of S will be L, and then di over dt. When you integrate, when you take Laplace transform of derivative, it turns out to be Ls I of S. If you compare this equation to this one here, we have voltage on the left-hand side, we have I on the right-hand side, and Z of S is equal to what in this time, Shabab? Z of S will be equal to what? Anybody tell me Z of
LS.
what?
LS.
In this case, the impedance Z of S will be equal to L times S. And if we go back to our table that I gave you last time, and I told you we can go back to it, we had defined the impedance like this. The internet is very slow and I don't hear you. I'm sure that one or two gave me an answer, but I don't hear anything. The internet today is very slow from our side.
Doctor.
I don't hear any of you, Shabab. If you just raise your voice.
Doctor, do you hear me?
Yes, alhamdulillah. And I hear you. شوفوا شباب here, when we bring the impedance, we found that the impedance for the capacitor is ZC is equal to 1 over CS. ZR is equal to R, and ZL is equal to LS. So these are the impedance for the The capacitor is 1 over CS. For the resistor is just R, and for the inductor is this one. It's just taking Laplace transform of both sides of this equation. Now, here, if we take Laplace transform of this one from the first relation, if we take Laplace transform of this, it turns out to be V equal 1 over CS I of S. And this is your impedance is 1 over CS. Now, if we take Laplace transform here, V will be equal to R I of S. So R will be your impedance. And here V will be equal to LS I of S. So the impedance will be LS. And this is the impedance method. We study the impedance method. It's very easy. فارس الزهراني تفضل.
دكتور ليه ناخذ اللابلاس ترانسفورم في الكاباسيتور والريزيستور؟
Here to show you the impedance method, to show you that this method is very easy. And now I will solve some problem using the impedance method to show you that this is very easy. Easy method. لأنه they are in time domain. هم they are in time domain. وإحنا الهارت of the lecture of the course نفسه is Laplace transform. يعني القلب النابض حق الكورس هو Laplace transform. Well, that's why we are using the impedance method to show you a simple method to study. Now I showed you how to find these methods in time domain. I will show you now how we can find them using the impedance method. The internet is very slow from our side. I don't know where you are or how is your internet. So we solved this one, Shabab, using the impedance, using the normal procedure, KVL. Now I will show you how do we use the impedance method. It's very slow. The pages are not turning quickly as I wish. المهم شباب, if we have, usually we write this, we try to bring the circuit you have in this formula. If we have, for example, here Z1, we have seen Z1 here and Z2 here, impedance here. So Laplace transform of this one, if you take Laplace transform of the output over the input, Z2 I of S, this is the output. And then the input will be simply this one, you add this one, Z1 I of S plus Z2 I of S here, and you will get the output over the input is simply Z2 over Z1 plus Z2. To use this method or to use this formula, the output over the input is the Z2 over Z1 plus Z2 directly. And it goes with, you can calculate it as you can see, the voltage here and the voltage here is, what is it? So you simplify I with I and you get this is the relation. Now, if you have a circuit like this one, see how much time it took us to find the relationship between the output and the input. If now we consider that L and R represent Z1. So Z1 in this case, it will be LS plus R, Z1. Z2, it will be 1 over CS. Now, if we take this formula, E2 over EI, the output over the input, it will be Z2 over Z1 plus Z2. Z2 is defined to be 1 over CS, as you can see here. And then Z1 plus Z2, it will be LS plus R, this is Z1, plus 1 over CS plus Z2, which is 1 over CS. This, you simplify CS with CS and you multiply CS by L. It will give you LCS squared plus RCS plus 1. You are done. In one short or in one step, you are done. There is no need to go find the inner loop and then find the outer loop, and then find the the Laplace transform, and then find the ratio. It gives you directly the formula. And this is Faisal Faris Zahrani, who asked me why we are taking Laplace transform to find the transfer function or to make your life easy. We have seen so far in Laplace transform, it's very user friend tool that we are using in this course. Any question regarding this one, Shabab, this problem? Any question regarding this problem? Is it clear? Any question, please? So, Shabab, here, if we have another problem like this, it starts becoming complicated. Obtain the transfer function E0 over EI for the electrical system shown here, using the complex impedance approach. Sometimes he asks you to use the specific method. You either use KVL or use KCL or use the impedance method. Here now we try to bring it to a form that to the previous form. No matter what is the circuit, try to bring it to this form. Now we have a Shabab R1, and we have C1, R2, and then C2 here. We call it Z1. We call this one Z2, and then we call Z3, and then Z4. Well, it's clear for you, it's clear that Z1 is R1, Z2 is C1, and Z3 is R2, and Z4 is... You can also write it this way, Shabab. You can also write it in this form. Here, remember, many students make a mistake. The output voltage here is across Z4. Remember this. The output voltage is across Z4. Here, from here to here is Z4. So what I am doing here, I am calling it this. The current passing through is I1 through Z1, and then the same current will go here. It will split into two current, I1 and another current, I2. So I1 and I2. This current, I1, goes through Z2. So I is equal to I1 plus I2. I here is equal to I1 plus I2. This is I2 here. So this is I2, and this is I1, and the current passing is this one. So we can write it like this here, and we take the output, the same current passing through Z3 and Z4 is I2. You look here, and here is the same. And we are taking the output cross Z4. It's the same. So I did not change anything. I'm just trying to write it in a convenient form to use the impedance formula. So now I can say Z2I2 here. I can say that Z2I1 here is equal to the inner loop inside loop. If you take this loop here, Z2I1 is equal to Z3 plus Z4I2. This one corresponds to, and we have I1 plus I2 is equal to I. This is what I am taking this here. And now if I solve for this equation, because I have I1, I2, and I. Now if I solve I1 for I1 and I solve for I2, I will find I1 is equal to Z3 plus Z4 over Z2 plus Z3 plus Z4 in terms of I. And I2 will be Z2 over Z2 plus D3 plus D4 in terms of I also. Now EI, the input voltage, will be Z1 times I plus Z2 times I2 in the inside loop. This one for the inside loop here, I'm writing it, EI will be Z1 times I plus Z2 times I1. Now, if I simplify, or if I substitute I1 from here to here, this is I1, I will write Z1I plus Z2 times this one. So I have everything in terms of I here and I here. Now EI, I can simplify it. So after that, it will get simplified here. E naught is equal to what? E naught is Z4. E naught is equal to Z4 times I2. I substitute I2 by its equivalent I, I2 by I. So I find the relationship between E naught and I. Now, if I take the ratio, output over input, it will be Z2, Z4 over all this one. Now, if we substitute what is Z1, what is Z2, what is Z3, what is Z4, you end up by having the same equation we have found before. 1 over R1 C1, R2 C2 S squared, plus R1 C1, plus R2 C2, plus R1 C2 S plus 1. So it's straightforward to use the impedance method rather than using the direct method. You can use any method you like, KVL, KCL, or the impedance method, but if the instructor forces you to use a specific method, you have to use the specific method. This one is easier to do once you know it, because it is systematic. Analogous system, Shabab. What do we mean by analogous system? It's sometimes, Shabab, it's very difficult to deal with mechanical systems. You need to do experiments with a mechanical system, bring a spring, bring a dashpot heavy, bring a mass that is very heavy to handle, and so on. So what we do, we see if these have equivalent in electrical circuit. So this is the spring. We do the exact experiment, we do it with electrical elements. Electrical elements, as you have seen, just circuits. And if you buy a resistor or a capacitor, it's about 2 gram or 3 gram, 5 gram maximum. So it's better than handling 100 kilogram here, or 20 kilogram here, or 50 kilogram here. So since it's very easy to handle with, we do equivalent analogous system. Analogous system, if we write here, Shabab, if we write our equation for this system here, for example, this system here, the equation of motion is simply mass times the output acceleration, d square x over dt square, plus b dx over dt plus kx is equal to p of t. This is for mechanical system. For the electrical system, we can write it like this: L di over dt plus, we have resistor, plus Ri plus 1 over C integral I dt is equal to EI. This is the electrical circuit. We know, Shabab, we have seen that Q is equal to di over dt, or I is equal dq over dt. I is equal dq over dt. So di over dt will be L square d square q over dt square plus Ri plus R dq over dt plus 1 over C integral I dt. When you integrate dt, معناته this one will be what? Plus R1 over C Q is equal to E. Now, if you compare the two equations, we have second derivative here. First derivative here, first derivative here. Variable here, variable here. In a clean picture, this will turns out to be like this. This is what it is. We have the secondary, we have the mass, we have L. Second derivative here, second derivative here. We have B, we have R. We have first derivative, first derivative. We have K, we have K, we have 1 over C. we have the variable, we have... Now, if you compare this, because they will have the same behavior, they will behave in the same way. So if we compare these two, if we make the comparison, we will say, oh, if we have translational element, this is the force will correspond to the voltage V. The mass M will correspond to the inductor L. The viscous friction B will be exactly the same as the resistance. Spring constant K will be the reciprocal of the capacitance. And the linear displacement X will be angular charge Q, and the voltage V will be the current I. Oh, sorry, the velocity V. Here, this is the comparison. So we can do our experiment in exactly the same way we do it for electrical system. And we are safe. They will behave in the same way. That's why we use the analogous system. And I give you the example for translation, but it's valid for rotation also. You can have the same thing. Torque will be voltage and it will be force here. Moment of inertia will be mass and it will be inductance. Viscous friction B will be exactly the resistance and so on. So this is for torsional system or rotation, and this one will be for a translation, and this one the electrical system equivalent. That's why we make the analogy muqarana. It's very easy to handle electrical components rather than handling with mechanical components. If we were having contact face to face, I would give you a small project in which you can just bring board and small circuits, and you will do the experiment. Any mechanical experiment, you do it through the electrical board, and you will see that it behaves in the same thing. That's why people nowadays, what they do experiments in electrical circuit, and basically they don't go up to electrical, they just go it with the Simulink. The Simulink, they will connect element. I will show you, inshallah, maybe next week or the week after, how we can bring electrical circuits. We connect them together and we have our experiment done. Once you are satisfied with the experiment, with the output, with the input, with all varying the parameters, you go and do it physically on real life. You do it on, this is what we call identification. You do it first on Simulink, see the experiment, see the variables, see the behavior, see the response, how to control the response, see what you are looking for, how to change the parameter, how to tune your experiment. When you are satisfied with it, go and do it in real life experiment. So I will stop here for today, and we will continue, inshallah, for the modeling of electromechanical system when we introduce electrical system to conduct mechanical response or mechanical behavior. If you give me just 1 minute, I will take the attendance, and then we will release you, inshallah. If you have any question, please. I'm trying to post the solution for quiz number 2, but system is very slow. Within half an hour, inshallah, I will be able to download the questions. Al-Alwa Munir, he's with us today. Al-Alwa Munir. منير كيف حالك؟ الدغالبي فيصل كيفك؟
الحمد لله تمام. كيف حالك دكتور؟
الله يبارك فيك. جاكم الويكاند ترتاحوا، استراحة المحارب الذي لم يحارب. جالس على الكنبة
والله حاربنا في الكويز يا دكتور.
يا عمي اذا تسميه كويز انت هذاك فيري سيمبل، ما في شيء. جالس في الكنبة وتشرب في الشاي ومنها وجالس المسعودي عبد العزيز موجود؟ عبد العزيز كيفك اليوم؟
الحمد لله. كيفك يا دكتور؟
الحمد لله. الملا ماجد موجود؟ You have any question بالنسبة لمحاضرة اليوم شباب؟ any question؟ قحطاني حسين كيفك يا حسين؟
خير نحمد الله.
الحمد لله. المحمدي عبد العزيز، أهلا شيخ.